Hi everyone. This video is for the Osmosis and Tonicity Lab in our cellular biology section. So make sure you open up your procedure and read it all the way through, and I'm going to go through it with you. So starting in part A, we are going to do a review of the big four macromolecules. So that's going to be our carbohydrates, proteins, lipids, nucleic acids. Those are the four macromolecules that we're talking about for this course. Now it says they are the utmost importance for life as we know it. Carbohydrates, nucleic acids, proteins, and lipids all play an integral role in our structure and in the functioning of the body. Not all of them are polymers. Now remember, one of those four cannot make a polymer, and of the other ones, sometimes they're not always in their polymer form, but they are all carbon compounds. They are all organic molecules. Remember, polymers are large repeating chains. The monomer is the building block, so a lot of monomers bonded together will make a polymer. The subunit is not an atom, but instead a molecule, an actual group of atoms bonded together. So keep that in mind as you go. Now, number one, it says write the name of the macromolecule to match it with the proper description. So read the description, write down what you think it is. Number two, lipids are mostly made of carbon and hydrogen, and they're generally insoluble, meaning they will not dissolve in water. So think about when you put oil in water, they don't mix very well. That oil is a lipid. It does not dissolve. It is not soluble. So some common categories of lipids might include fats, oils, or waxes. A steroid is also a lipid. Many lipids are formed when a glycerol molecule combines with three fatty acids. Three fatty acids, think triglyceride. So as you can see from the diagram, a lipid does not have a molecular repeating subunit, so it does not have a polymer, and therefore lipids do not make, it does not have a monomer, and so therefore lipids do not make polymers. Now looking at the picture, it wants to know, is this lipid saturated or unsaturated? So remember, when we use the term saturated, it means that it has as many hydrogen atoms as it can possibly hold. So it all has to have carbon to carbon single bonds. It needs to be an alkane. Remember, alkenes and alkynes with our double and our triple bonds are unsaturated because they end up having the double or triple bond between a carbon, which means you need to remove hydrogens. You can only have 4 lines or 4 bonds with every single carbon atom. So looking at this picture, is it saturated or unsaturated? Write that down. Now this here is a picture of a triglyceride. Okay, so we see our 3 long chains of carbons, and then we see glycerol on the end. So on the left side, that vertical thing is called glycerol. It's just the type of molecule that these fatty acids are bonded to. And I'm sure everyone's heard of triglyceride. It's something they test in the blood to help measure your health. But there are a lot of different types of lipids. Triglyceride is just one of many types. Lipids can be saturated or unsaturated. Now it says lipids that are saturated have all the hydrogen atoms that they can hold on their carbon atoms. Therefore, they only have single bonds. They are considered an alkane. Remember, if there are double bonds on 3 of the oxygen atoms, we don't really count that, right? When we talk about alkane, alkene, and alkyne, we're simply talking about between carbon to carbon atoms. So the double bonds with the oxygen doesn't change if it's saturated or not. We're just looking at carbon. Saturated lipids are generally solid at room temperature and do not have a kink in them, so they stack well and block passageways. Let me show you what that means. So do you remember we said when we draw out these long hydrocarbons, we could draw out every single carbon and every single hydrogen, but there's a shortcut that I showed you in the covalent bonding lab. Well, that shortcut, if you recall, really just a bunch of mountains and valleys, peaks and valleys, as I like to say. So this right here is heptane, because I have 7 peaks and valleys, right? So at the end of every single line, here, 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 those are all carbons. So I can count, I have 1, 2, 3, 4, 5, 6, 7 carbons, and these all are single lines, meaning it's a single bonded alkane. 7 carbons is heptane, so this is heptane, okay? This is saturated, right? All single bonds. This is what it means when it says that there's no kink to them, okay? Now, if I have a lot of these, all kind of in the same area, they can actually fit together quite nicely like puzzle pieces. Okay, so you can see how these might clump together, fit together, and they can actually block passageways. Saturated fats are considered not as healthy as unsaturated fats. Okay, so when we think of food, when we think of nutrition, eating a saturated fat is less ideal. Saturated fats are fats that are solid at room temperature, like animal fat, okay? Unsaturated fats, on the other hand, typically are plant fats, tend to be liquid at room temperature. Why? Why the difference? Well, if they're unsaturated fats, that means that they somewhere have a double or a triple bond, right? So if there's a double or a triple bond, that's actually going to change the orientation. And it means that they're going to be much harder to clump. So here I have some alkenes. I have my double bonds, right? I just need one double bond to make it an alkene. And you can see that when I end up with that double bond, it actually changes the molecule shape. It gives it a kink, we say. So they don't fit together nearly as well as our alkane fats, okay? That's why unsaturated fats, those with a double or a triple bond, tend to be liquid at room temperature. Olive oil, peanut oil, canola oil, right? The animal fats are saturated fats. Also coconut oil, right? Coconut oil has a balance, but if you notice, it solidifies pretty easily around room temperature. So usually around below 70, you'll see it being solid. That's because it does have some saturated fats. Now it will turn into a liquid, it does have some unsaturated fats as well, okay? So when we think of saturated versus unsaturated at room temperature, think of how they would react in the body as well. So sometimes our saturated fats will fit together really nicely and they can form clumps and blocks in the arteries. Pretty neat. So it says, if there's a double or a triple bond, to make a kink in the molecule, it can melt at a lower temperature. Okay, those molecules are going to move apart easier, they're going to become fluid. This type of lipid is usually liquid at room temperature. And then some more examples, unsaturated fats are typically our plant-based sesame oil, corn oil, etc. So I've told you this, right? Which one is considered better for human consumption? Lipids are only one of the 4 macromolecules, okay? But out of those 4, it is the only one that cannot form a polymer. True or false? And think about why. Why do you answer the way that you do? Now, number 3, carbohydrates are composed of carbon, hydrogen, and oxygen. Okay, remember there's a ratio that they follow for those. How many simple sugars makes up a monosaccharide? So remember, saccharide is our root word for carb, okay? So monosaccharide. How many sugars make up a monosaccharide? Next question, how many simple sugars bonded together make up a disaccharide? And a polysaccharide is formed when many monosaccharide molecules are bonded together. Starch is an example of this, an example of a polysaccharide, okay? What is the monomer for starch? Okay. This is all just a review of some of the chapters we've talked about with these macromolecules. Number 4, nucleic acids contain hydrogen, oxygen, nitrogen, carbon, and phosphorus. Nucleic acids are polymers. Nucleotides are the monomer or the building block. What are the 2 types of nucleic acids? And then number 5, DNA holds the code that determines which proteins we synthesize in the body. And the proteins are then what does all the functioning of the body. Proteins are composed of nitrogen, hydrogen, oxygen, carbon. What are the monomers for protein? Protein is the polymer. What makes it up? What is the monomer? Okay. Now it says the order of these amino acid monomers is determined by the DNA. Okay. Proteins, they do a lot in the body. They form muscle. They help form bone. They are the enzymes that help reactions occur. So enzymes are really great in reactions because they do something called lowering the activation energy. Enzymes lower the energy needed to get a reaction started. So they help chemical reactions occur faster and more easily. Those enzymes are proteins. Pretty neat. We use enzymes all throughout our body because our body is always doing chemical processes. Okay. Now, the neat thing about enzymes is that they're not actually used up by a reaction. They're not changed as they go from the reactant side to the product side, meaning we can reuse them over and over again. Okay. Now, it says these enzymes are necessary for reactions to occur within the body. For example, the sugar in milk, lactose, okay, OSE means sugar, lactose is a sugar that's broken down by an enzyme called lactase. When we see ASE, that is the ending for an enzyme. So lactose, the sugar, is broken down by lactase, the enzyme. Okay? Most humans decrease the production of lactase as they age, and they're no longer drinking mother's milk, and so they may become intolerant to lactose, which means that they don't have enough lactase in their body or enough of the enzyme to break it down. So that's why you can find different milks or different supplements like Lactaid that will help people digest milk. It actually has the enzyme lactase that will help them digest and break down lactose, the sugar. Okay? All right, now part B. This is where we get into our experimentation, and it's a pretty straightforward one today. It says the inside, outside, and the membrane. Well, there's no one standard size for a cell. Most cells are very small. Okay, prokaryotic cells are cells that do not have a nucleus. They belong to bacteria and archaea. So bacteria and archaea are under the prokaryotic umbrella. They're more ancient. They're older cells that were around when the first life on Earth began. And since we have evolved and created some eukaryotic organisms as well, which is what we are. So prokaryotic cells, those ancient bacteria and archaea cells, are typically very small. They range from 1 to 10 micrometers in size, pretty tiny. Eukaryotic cells, on the other hand, we do have a nucleus in eukaryotic cells, and they tend to be a bit bigger. So the different classes under eukaryotic are going to be protists, fungi, plants, and animals. Our eukaryotic cells range from about 10 to 100 micrometers in size. Okay. Now again, that will vary, different sizes of cells for different types of cells, right? Eukaryotic cells have membrane-bound organelles, while prokaryotic cells do not. Prokaryotic cells have a membrane on the outer part of the cell, but they do not have membrane-bound organelles inside. Okay, their DNA is just floating around. It's actually in a circle formation, but it's not contained in the nucleus like eukaryotic cells. For eukaryotic cells, we have a nucleus. Our DNA is inside the nucleus. Okay, now along with that nucleus, we also have a whole bunch of different equipment in the cell that helps produce proteins, all sorts of things. And so those are called organelles. Those organelles are actually bound by membranes as well. All right. So it says eukaryotic cells have membrane-bound organelles like the nucleus, like the mitochondria, like the Golgi body, like the endoplasmic reticulum. And so they're generally larger and more complex. A human skin cell, for example, is about 30 micrometers, but a red blood cell is only about 8 micrometers. Okay, red blood cells are one of the few cells in the body that actually lose their nucleus as they age. They start out with it and then they lose it, so they're a little bit smaller. Okay. Now, most cells are too small to see with the unaided eye. There are, however, some exceptions. So an egg, for example, you can actually see with the naked eye. The human egg is actually about the size of a period on a piece of paper. You probably would never see it, but in theory, you could. Think about a chicken egg, though. Well, that you can certainly see. A chicken egg is just one cell, right? Pretty neat. There's another thing called an amoeba, right? An amoeba is a very type of ancient single-celled organism, a prokaryotic cell, and that certain type of amoeba can actually be up to 4 inches long. So again, usually cells are small, but sometimes they can be quite large. The cell membrane is the barrier on the outermost part of a cell. Okay, we consider it the gatekeeper between the inside and the outside. It dictates what can come in and what can go out. It is semi-permeable, meaning only some things can permeate, or you could say selectively permeable, right? It's selecting what can go in and what can go out. And of course, it's not thinking about it and deciding. There are some biological and chemical factors that will determine what comes in and what leaves the cell. Okay? Some of that is size, some of that is polarity, some of that is if energy is available to help it move across. A lot of different things that we'll talk about in our membrane sections. So what happens to a cell when the inside and the outside environments are different, right? The neat thing about a cell membrane is it can help keep the inner chemical environment very different and very separate from the outer chemical environment. But if they're different, sometimes things will change to help it adjust, to help it maybe reach some type of homeostasis. So that's what we're going to explore with this lab. You will need a cucumber, so that is your grocery shopping list item. You'll also need some table salt. You're going to need your beakers. So if you have 2 beakers in your lab kit, go ahead and get those out. Tap water is fine to use for this lab. You'll also want your scale or your balance that came in your lab kit. And you might want a weigh boat, which would just be your coffee filters from the lab kit. And then of course you're going to need a cutting board and a knife to actually cut up your cucumber. And you'll start out with your food coloring bottle as well. Okay. Now this first part's pretty straightforward. It says fill a beaker most of the way with water. Place a drop of food coloring in the water and observe what happens. Okay. What did the food coloring do? When you dropped it into the water, what did it do? And what did the water do? Write down your observations. Now, number 2, it says, well, most people see that food coloring diffusing, spreading out, right? But what about the water itself? It's a little bit harder to see what happens to it, but think about it, right? If we're putting food coloring into the water's space, what is the water going to have to do? Diffusion is the net movement of particles from an area of high concentration to low concentration. Okay. Now we said that the food coloring diffused. So what that means is when you put a drop of food coloring in the water, it starts out with a very high concentration of food coloring in that drop. But it's now going to go from an area of high concentration to low concentration, the water being the low concentration, right? When you put that drop in, there's no food coloring in the water. It has a 0 concentration of food coloring. But the drop has a very high concentration. So it's going to diffuse. The food coloring is going to spread out and disperse itself through the water. That's diffusion. That happens naturally. Think about flowers in a room. If you bring in a very fragrant bouquet of flowers, they're going to smell the most strong up by the blossoms. But if you let them sit for a little bit, all the way across on the other side of the room, you're going to start smelling the flowers, right? Slowly, that scent, the scent particles, are spreading out through the air. They're diffusing through the air of your room. So think about that with food coloring and think about what happens with the water. Did the water diffuse? Now it says, since there was a high concentration of food coloring in the drop, and then it spread out into the water, the food coloring diffused. Okay, that doesn't require any energy. It's simply just the natural movement of the particles. Or I should say it doesn't require any additional energy because the movement of the particles is called kinetic energy, if you remember from the beginning of class. So the particles in the food coloring and in your water have that natural kinetic energy. They're constantly moving. And so when you put the food coloring in, those particles are going to start to bounce all around and they're going to spread out. It doesn't take any extra energy for diffusion to happen. we say it's passive, right? It's a passive mode of transportation, of movement of particles. But since water went into the food coloring as well, where there was a low concentration of water, right? So flip it. The drop diffused where there wasn't any food coloring, right? But the water can also diffuse where there isn't any water. So when you put in the food coloring, there wasn't any water in the drop, so the water can move into that space. So the water is in fact diffusing as well. They're going in opposite directions, but both liquids are going to be diffusing or moving their particles from high concentration to low concentration. Now it says the diffusion of water or other solvent is so important that it gets its own name. It's called osmosis. So the diffusion of water is called osmosis. Remember, water is considered our universal solvent. A lot of things can dissolve in water. And so life depends on the presence of water. Okay, we need to make a 0.1 molar NaCl solution. Remember, molarity is the concentration, so we need to make a saltwater solution with a 0.1 molarity. Now it says you can do this by putting 0.1 moles of NaCl into 1 liter of water, or you could do half. You could put half of 0.1 moles of NaCl into half a liter of water. There may be other things in your table salt at home, but try to use the most pure one that you can. So don't use garlic salt or any type of seasoned salt. If you just have basic table salt, try to use that. And we're going to assume that it's as pure as it can be for our at-home lab. Now here's our equation for molarity. Molarity equals the moles of solute, or the number of moles, divided by the liters of water. Okay. Now this is going to walk you through how you need to figure out how much salt to put in your solution. So to make a 0.1 molar solution of salt water, you need to figure out how many grams of salt to weigh out to add to your water. Now it says, what is the mass of 1 mole of sodium? Okay, now remember, by definition, 1 mole is equal to the atomic mass in grams of that certain element or molecule. So what is the mass of 1 mole of sodium? Well, all you have to do is use your periodic table, find sodium, look at the atomic mass, 22.99, and remember that 1 mole is equal to the atomic mass unit in grams. So what is the mass of 1 mole of sodium? Well, it's 22.99 grams. Pretty easy, okay? What is the mass of 0.1 mole of sodium? Well, we have the mass of 1 mole up above. To get to 0.1 mole, we move the decimal point over to the left, 1 spot. Okay, write down that answer. In grams, what is the mass of 0.1 mole of sodium? Just move the decimal point. We're going to do the same thing with chlorine. What is the mass of 1 mole of chlorine? Well, use your periodic table, find the atomic mass unit, and remember that the 1 mole of an atom is equal to the atomic mass of it in grams. Okay. Now the same thing for chlorine as well. 0.1 mole of chlorine, what is that in grams? Remember, we just have to move the decimal point 1 spot. And then the last question, it says, what is the mass of 0.1 mole of sodium chloride? Well, take your 0.1 mole of sodium and your 0.1 mole of chlorine and add the masses together. How many grams do you get for sodium chloride? Okay, that answer is how much salt you're going to be adding to your water. Nice and simple, okay? Now we're going to start doing the experimentation, so make sure that you have all of your equipment out and you're ready to go. And then go ahead and start the experiment. You're going to want to use your scale, so make sure you add your batteries if you haven't used it yet. Make sure you have your cucumber out, your cutting board, your table salt, everything ready to go. I'm going to hop into my lab and then we'll walk through it together. Okay, here we are in my lab, and I'm going to start to weigh out my salt. So you should have a little pocket scale in your lab kit. It might look something like this. You want to make sure you put your batteries in the back. And then there's actually a button on the side you push to remove the cover. Okay, I think this thing is really cute. So here's your little scale. And this cover can actually be used to put on top to help you have more room to weigh things. Kind of cool. Yeah. You'll notice you have a button to switch between units. We're going to want to be in grams for this part. We have our on-off button and our tare button, which is going to be incredibly important today. So set up your little scale. I'm just going to measure directly on this, make sure it's nice and clean from debris. But you could also use your paper filters if you want. My problem with these is they're a little bit large. So you just want to make sure when you weigh things that you don't have anything coming off of the actual scale, okay, off of the metal part, which these seem a little bit too big for my case. So you could, I suppose, put them on top of this, and then it should work just fine. But I'm going to measure directly on this. So choose how you'd like. Okay. I'm going to turn my scale on. And I'm going to make sure that it's at 0. Now, if you didn't have this on to begin with, say you're just putting it on now after your scale's already on, you're going to have a measurement on there. So you're going to want to hit tare and make sure you're at 0. Okay. Make sure that you see a gram or a G in the bottom right corner to make sure that you're in the correct unit. Now the number you got in our problem up above for what is the mass of 0.1 moles of sodium chloride, that's how much you're weighing out. Now remember, it's going to be in grams, okay? So I'm going to weigh it out as best I can. I only have 2 decimal points or to the 100th of a gram on this. Which is actually pretty good for a scale. Almost there. Now your procedure says if you weigh out too much, remember you shouldn't put it back in the container. It should actually go in the trash because now it's been contaminated by a lab. We never want to eat any of our material. I have just a pinch too much. And there we go. So this is the table salt I'm going to add to 1 liter or 1,000 milliliters of tap water. Okay, now my beakers are not quite big enough. Okay, my largest beaker that I was given is 400 milliliters. So I'm going to use this and I'm going to measure out 1,000 milliliters and I'm going to put it into a larger container. I'm actually just stealing my husband's coffee Chemex thing. Maybe you have a pitcher you can put it in. If you don't have a container that's large enough to mix up some salt water, just do half. Okay, so take your number you got in the problem up above and divide it by 2, and that's how much salt you want to weigh out. And then you just need to put it in 500 milliliters of water. Okay, now we are going by milliliters, so make sure to use the milliliter mark on your beaker. And again, tap water is just fine. So I'm going to go fill up some tap water, and I'm going to add 1,000 milliliters to my larger container. Okay, I have my liter of water. I'm going to add my salt to the water. I don't think the procedure says this, but you want to make sure that you stir it up so that it's nice and uniform. So you can give it a nice swirl, or maybe you get a spoon. And make sure you stir from the bottom for a little while, because that's where all of the salt particles are what I want to settle to. And remember, we're trying to get it to dissolve. Stir it up nice and well, okay? Now the next thing you want to do is you want to take your 2 beakers and label them. So you're going to have one labeled tap water and another labeled salt solution, okay? That way you can make sure to distinguish which is which when we do our experiment. So your 2 beakers, go ahead and get some tape and some paper and label 1 regular water and 1 salt solution. Okay. I have my labels on my beakers, and now I want to put in 250 milliliters of each one. So 250 milliliters of just tap water and 250 ml of your salt solution that you've made. So I'm going to go ahead and fill this up. Again, just tap water is fine. And hopefully everyone has beakers that are large enough. My smaller beaker only goes to 250, so it's a little full. And then for my salt solution, 250 as well. And again, remember you want to be looking straight on when you take a reading of something. And if you want to be very precise, it's best to let it sit and then look down at it. Okay, so I have 250 milliliters of regular water and of my salt solution. I have each one labeled, and now I want to actually cut my cucumbers up. So you just need 2 slices of a cucumber, not very much. You want each slice to be about 1 centimeter thick, so you can use your ruler to be nice and precise. Try to get them as close to each other as possible in their thickness. And then it says that you actually want to cut out the seeds in the middle. So you're just going to end up with a ring of the fleshy part, not the seeds. Okay. And you can just toss those. So I'm going to go ahead and cut out my seeds of my cucumber. Now you can use a regular cucumber. You could use a little pickling cucumber or a mini cucumber. You could use an English cucumber. That's what I have. Might be a little too early, but maybe you have a cucumber from your garden. It doesn't really matter. Okay. All right, so cut out the seeds as best you can. This is about your thickness that you want. And you want to have 2 paper towels for each of your beakers. And you're going to put a cucumber in front of each one. Now be careful not to accidentally swap cucumbers. Okay, we want to make sure that they stay in their distinct locations. And what we're going to do next is we're actually going to start dipping the cucumbers in the water. Okay, now we want to keep as much of the cucumber exposed to the water as possible. So if you have tweezers, that might be a really nice way to dunk it in. Okay, wiping the tweezers between each. But you can also just grab it with your fingertips. But do just use your fingertips and don't do a big old hold over it. Okay, just grab the edge as best you can, and you're going to dunk it in and pull it back out. It just says quickly, so try to be consistent each time you do it. Okay, consistency for a lab is great, right? Now it says quickly dip the first cucumber into the water and set it on the water paper towel. Gently dab it with the paper towel and take the cucumber's mass on your scale. Okay, record it on the chart for time 0, and then repeat with your other cucumber. So you're going to dip that cucumber in the salt water, set it on the salt water paper towel, and record the data. You might want to label your paper towels, or maybe you just leave them right in front of your beakers, and that's fine too. Okay. So make sure you have your scale ready to go. I'm going to get all the salt off from when I weighed my salt. I don't want that to affect my data. Okay. And we're going to record this all in grams. Okay, now just a quick dip. So here's my regular water. I'm going to dunk it. And you don't need to really dry, you just want to patly gent. Okay, gently pat. There we go. Quick dunk. Maybe you shake it a bit and gently pat. Okay. Take your mass, record it on your table. And now I'm going to do the same for my saltwater saltwater cucumber. And I'm going to record that on my table. Okay, leaving them on their paper towel in front of their water. Now you're going to start a timer. Okay, so this was time 0. Now you want to set a timer either on your phone or a kitchen timer for 3 minutes. Okay, so 3 minutes, you're going to record different things and put it into your timer or into your table. So here's what it says. After you've dabbed your cucumber and you've taken its weight, you want to record this for time 0. Step number 9. Place the cucumbers all the way into their respective solutions and start a timer. Okay. Every 3 minutes, remove the cucumbers, gently dab, and record the mass. Make sure your scale is taired before you put the cucumber on. Okay. And so you're going to end up taking a mass until you get to 21 minutes. So until your cucumbers have been soaking in there for 21 minutes. All right. Now I'm going to go ahead and get my phone so I can start my timer. Now time 0 is what we just did. So I'm going to have my phone beep at me every 3 minutes. Okay. And I'm going to put these cucumbers in and then start my timer. Okay. So they're now floating in my solutions. My timer is going. And when it beeps in 3 minutes, I'm going to take them out. I'm going to gently dab. And then I'm going to weigh each one. And then I'm going to put them back in, start my 3-minute timer again. Or maybe you have one going continuously. I'd suggest only doing it in 3-minute marks so that you have time to dab, to weigh without affecting your data. Once you get to 21, you can stop your data collection. All right, so go ahead and pause the video, continue with your cucumbers. I'm gonna let mine soak for a little while. But once you've finished, come back to the video and we'll continue. Okay, so now if you've reached your 21-minute mark, you've completed your table, you can go ahead and clean up. So the cucumbers can go in the trash. Your salt water and tap water you can just pour out. Make sure to rinse your beakers and any containers that you've used or spoons. And then go ahead and put your scale in the off position, cover it, and put it away for safekeeping. Okay, again, we want to keep our beakers and any equipment that we used so we can keep them available for future labs. Now you're going to graph your data. Okay. You're going to put time on the x-axis or the horizontal axis starting at time 0 and going up to 21 minutes. Okay. Your y-axis is going to be your weights. It's going to be your gram amounts that you are getting on your scale for your cucumbers. I highly recommend using 2 different colors to do this. One for your water-only cucumber and one for your saltwater cucumber. So you should end up with a line graph with 2 lines, hopefully each one in a different color to help you see it. All right. There is graph paper included for you if you need it. You can also do it by hand and upload it that way. All right. Once you've completed your graph, we're going on to number 11. Now it says calculate the percent change for your cucumbers. Okay. So you've noticed there was a change in the mass of your cucumbers. We're going to calculate out how much they changed in terms of percents. So if your answer is positive, it was an increase in mass. If your answer was negative, it was a decrease in mass. Be sure to state the percent change with an increase of X% or a decrease of X%. So if you get a negative number, you don't need to say negative whatever. You would just say a decrease of. Okay. Here's the formula to find percent change. You're going to take the new value minus the old value divided by the old value. What does that mean for this? Well, your old value is times 0. Your old value is how much the cucumber weighed before you did any experimentation with it, when you just simply dunked it in the water and weighed. Okay. Your old value is the times 0 mass. Your new value is going to be your 21-minute mass. So after you've let it soak for 21 minutes, take the new value as that mass. Okay. So your 21-minute mass minus your times 0 mass divided by times 0 mass, all times 100, we'll put it into a percent form. And in your box below, you're going to write it was an increase of what percent, or it was a decrease of what percent. Remember, I shouldn't see a negative for your percentage. Okay, now the analysis. What did this mean? It says solutions are uniform, or they're homogeneous, same throughout. Solutions, if you remember, have very small particles or solutes dissolved in the solvent. So they end up being mixed evenly. We don't have to keep shaking them or stirring them. They stay mixed within the solution. These substances are classified as either a solute or a solvent. Okay, so think about our sugar, our salt and our water. Which one was the solvent? Which one was the solute? It says the solute dissolves in the solvent. Water is a universal solvent because it can dissolve so many different solutes. So if we were to make sugar water, what would be the solute? What would be the solvent? Now it says some particles can move easily in and out of a cell membrane and some cannot. If a particle is large or it's charged, it can be difficult for that particle to move through the cell membrane and will usually need some extra help, maybe like a protein. There are proteins that help things go across the membrane easier. They either act like a pore, where things can just flow straight through, or they act like a gate where it will open and close. Okay. So if something is too big, or if it has a charge, positive or negative, it's going to be difficult for it to move to the membrane be difficult for it to move through the membrane on its own. When an ionic compound is dissolved in water, it disassociates, it separates into its ions, and the particles are then in the ionic form. Okay, so sodium chloride, NaCl, when it dissolved, what is it now? It's now in the ionic forms. So what are the ionic forms? Often the solutes in a solution cannot easily diffuse across a membrane, but water can. The cell membrane will allow water to enter or exit the cell in order to achieve balance between the internal and the external environments, homeostasis. So if the particles are too big to move, to diffuse, then water will move instead. What is the diffusion of water across a semi-permeable membrane called? This was given to you up above. And then it says which way the water moves depends on the tonicity of the solution. Tonicity is a measure of the relative concentration of solute particles. Okay, it's all about concentration. It's a measure of the concentration of the stuff, the particles, not the water, right? The water is the solvent. So we have three different tonicity terms that you should know. Iso, hyper, and hypo, okay? Iso means equal, hyper means above, hypo means below. So an isotonic solution is where the internal and external environments of the cell are equal. So an isotonic solution presents an environment where the concentration of solutes outside the cell equals the concentration inside the cell. There's no net movement of water. Okay. A hypertonic solution, on the other hand, is an environment where the solutes outside the cell are greater than that of the inside of the cell. So the net movement of the water is out of the cell. Okay. Hypotonic is the opposite. So a hypotonic solution is an environment where the concentration of solutes outside the cell is less than the concentration inside the cell. So the net movement of water will come into the cell. So again, if those particles cannot move across the cell membrane, water will. And think about it in terms of concentration. It's trying to equalize the concentration. So if I have a lot of stuff inside of my cell and not that much stuff outside, I want to have an equal concentration, okay? If there's a lot of stuff inside, well, I can add water to it, and that can help equalize, right? I can dilute it with water. Say you make some coffee and you put a teaspoon of sugar in it and it tastes way too sweet to you. Well, what can you do? You can add more coffee, right? That will dilute it. With your sugar water, if it's too high in sugar, you just add more water. It dilutes it. That's what's happening with osmosis. So if I have a lot of stuff inside the cell, water will move into the cell to help balance it out. And the same thing will happen in the other way. If I have a lot of stuff outside the cell, water will move out of the cell to try to balance the concentration, to try to dilute it. Now it says, notice the type of solution depends on how the outside conditions compare with the inside conditions. Diffusion is when molecules move from areas of high concentration to areas of low concentration. Diffusion does not require an input of energy. It just uses that natural kinetic energy. So it's like rolling down a hill, right? It's just happening on its own. The diffusion of water across a membrane is so important it gets its own name, osmosis. Now, you're going to complete the table. So put down what your percent change was for your water only and your salt cucumber. And then you want to decide, is this a hypo, hyper, or isotonic solution? So think of the cucumber as a cell, right? It does in fact have many cells, but pretend it's one big cell. Is stuff moving into it or was stuff moving out of it? And that stuff, of course, if we're talking osmosis, is water. Did water move into your cucumber or did water move out of your cucumber? And we can tell that by the weight, right? If it changed, if it increased in weight, if it got stuff into it, or if it decreased in weight, if it lost that water or that stuff. Complete the following table by placing the missing words in the last column. So you have evidence, you have a claim you're making, write down the missing word there. You want to think about the tonicity terms. Okay? And then number 6 gives you a nice visual of how this can be thought about. It uses red blood cells. Okay? So we have 3 beakers, each one with a single red blood cell in the beaker, obviously not to scale. Okay? And then you have blue dots, that's going to be your solute or your particles. And remember, the particles in this case cannot move across the red blood cells barrier. Okay, they cannot go in or they cannot go out. So if the blue dots, the solute, cannot move, water has to do it. So water is either going to stay for isotonic, it's going to move into the cell for hypotonic, and it's going to move out of the cell for hypertonic. When we think of things as being hyper or hypotonic, we're actually talking about the solution, not the cell. Okay? So something that is hypertonic has a lot of stuff in the solution. Which one is that picture? Which one has a lot of stuff or a lot of solutes in the solution? And if there's a lot of stuff in the solution, the water in the cell has to leave to try to help out. Now with hyper and hypotonic solutions, we have 2 things that could happen. The cell will either get really big, and it could swell and possibly burst. We call that lysis. Okay. Or the water is leaving the cell and it's shrinking like a raisin, it's shriveling up. We call that crenation. And then you have a little review to read, so make sure you read that. And there's a really nice video about a YouTube experience on YouTube. Okay. But be sure to open up that link and watch the video because it's a nice visual on how all of this works. All right. As always, have fun and let me know what questions you have.